Good afternoon, it is a pleasure to be here at JuliaCon. My name is Miguel Marcelino and I'm here to present our work on the PyJL transpiler, which translates Python source code to Julia. More specifically, we're developing it with the purpose of translating Python libraries into Julia. Now, before we start discussing PyJL, it is important to first motivate the audience towards this research, and I'll start by briefly introducing transpilation in general. Now, a transpiler, in its simple form, translates source code between an input language and an output language. As an example, consider the Fibonacci function on the left, which is written in Python. A transpiler that translates code into Julia could generate the following source code. Now, it is important to note that in Julia, we do not require the use of return in this last statement. However, this is included to remain consistent with the remaining statements. And this already gives you an idea of the pragmatics of the code that we're trying to generate. Now, our work focuses on the translation of Python libraries into Julia, but why did we choose these two languages? And let's start by introducing Python. And for our research, we will use CPython as it is the reference version. Now, Python has a clear advantage, its popularity. Currently, Python has a 12.2% rating on the TIOBE index, which is also currently the highest rating on TIOBE, and this popularity in turn largely influences its development. PyPy, which stands for the Python Package Index, registers more than 382,000 projects. However, as we all know, Python is slow on modern hardware, and furthermore, it also suffers from the two-language problem. And this brings us to Julia, and Julia's biggest advantage over Python is that it has high performance on modern hardware, and it is one of the 4 languages along with C, C++, and Fortran that belong to the Petaflop Club. Furthermore, it offers a math-friendly syntax, which makes Julia ideal for numeric and scientific computing. However, Julia also has its nuances. Its popularity is something to highlight when compared to Python, and this brings us to the most important aspect, which is that despite its good package integration mechanism, it still lacks some of the high-quality libraries found in Python. And here you can start to notice that Python and Julia are somewhat complementary. Now, as Python has a very large library set, it would be beneficial to translate some of those libraries to Julia. In particular, if we translate a subset of that library set using an automated translation tool such as a transpiler, then that could potentially speed up Julia's development. And this brings us to our proposal, which involves extending the PyJL transpiler, which is an open source transpiler that is part of Py2Many. Now, Py2Many has a generic framework which is the basis for many transpiler implementations, each transpiling Python to a different C-like programming language. As an example, there is PyRS for Rust, PyCPP for C++, and so on. And PyJL extends this framework and implements its own transpiler implementation to transpile Python to Julia. Now let us start by describing some challenges that we faced while transpiling Python source code to Julia. And this should give you an idea of the most notable differences between the two languages. Now, the first challenge we faced was the translation of operator semantics to Julia. Now, as an example, consider the following Python code excerpt which sums 2 lists. Now, initially, the transpiler translated this excerpt using the same syntax as Python. However, the result we obtain in Python is different from the one we obtain in Julia. Now, while the plus operator is used to concatenate both lists in Python, in Julia it is applied element-wise on both lists, and therefore both operators have different semantics depending on their operand types. Now, one possible solution that solves this problem is to map Python's plus operator to an equivalent operation in Julia. And by using this new syntax, both Python and Julia produce the same result. And this brings us to the translation of augmented assignments. For our next example, let us introduce a new variable z, which holds a reference to variable x. It is worth noting that Python's augmented assignments will perform in-place operations when possible. As an example, consider the following Python augmented assignment performed on variable x. Now, as we saw in the previous example, lists cannot be concatenated in Julia using the plus operator. And the syntax that we used previously to concatenate lists x and y will also not match Python's in-place operation behavior. Here we include a visual representation of the memory layout in Python after such an operation. Now, as Python follows the object-oriented paradigm, integers will also be represented as objects. If we observe the memory layout in Julia, we first notice that variables x and z point directly to the list's values, and this is because of how list x was initialized, which allows Julia to optimize memory allocations. However, the most important aspect is the fact that x now points to a newly generated list, while variable z still points to the original list. Therefore, the transpiler uses the append function to map in-place concatenation operations between two lists. And notice that the memory is now allocated similarly to how it is in Python. As another example, consider the following augmented assignment in Python. This operation requires the use of a specific function in Julia, which can be seen here on the right. And notice that the last operation uses a special syntax in Julia to insert the elements in the list instead of replacing them. And these examples actually introduce a much larger problem. Now, if operators are type dependent, then that implies that we must be able to infer the types of operands at compile time. But that is not always possible. For instance, take the following function that computes the Bonacci series. If we try to transpile this function into Julia, the transpiler will produce the following result, and this result is wrong. Now in Python, the first multiplication operation in the function will repeat the elements of the list m times, while in Julia it will multiply each element of the list by m. To correctly transpile this example, a programmer first has to annotate the arguments of the function, and with the annotated function, the transpiler has enough information to transpile it correctly. And notice how the assignment to variable a has changed to the equivalent operation in Julia. And for Py2Many in general, function definitions should always be annotated with the appropriate type hints to guarantee the generation of correct Julia source code. Now, arguably one of the most common mismatches that occurs when transpiling Python to Julia is indexing. And the most obvious difference is the fact that Python uses 0-based indexing while Julia uses 1-based indexing. And to demonstrate translation of indexing, on the left we have a Python implementation of the Newman-Conway sequence, and when we try to translate this with the transpiler, the initial result before any optimization process was the one seen here on the right. And as we can see, simply incrementing or decrementing the value by 1 does not produce pragmatic code. And in such situations, we resort to our people optimizer, which optimizes the quality of the generated code. Now, the people optimizer currently included in Py2Many optimizes redundant binary operations when they are detected in loop range calls, and also indexing. Notice how much simpler the code looks with this optimization. Now, the story somewhat changes when we try to translate negative indexing, and let us consider a simple indexing example in Python which uses negative indexing. Now, in this case, the indexing value is an integer literal, so the transpiler can translate this to the equivalent operation in Julia. However, if we use variables to hold the indexing values, for instance, the scenario changes. Now, for instance, consider that a is a variable that was defined before these operations, and in this scenario, it becomes impossible to statically determine if indexing is being performed with negative values. There is, however, one exception to this, where the transpiler is able to detect negative indexing, and we will come back to this later on in the presentation. Now, the last mismatch we want to discuss is arbitrary precision arithmetic. And as an example, let us consider the function main, which stems from a benchmark called PyDigits. And as the name suggests, this benchmark calculates the digits of the number pi. Now, the main function starts by reading the number of decimal cases up to which it should calculate the number of pi and initializes the variables that will be used throughout the program. Now, on the right, we can find the corresponding translation of this function to Julia, and as one can see, the result is very similar to Python. However, there is one mismatch, which is how Python and Julia handle arithmetic. In Python, arbitrary precision arithmetic is used on all operations, and this will be important in this example for the highlighted variables. However, in Julia, this is not the case, and therefore, when one uses integer literals, Julia will use modular arithmetic. And to show what happens, let's follow the execution of the function nextTerm both in Python and in Julia. Now, the function nextTerm calculates the next term in the sequence from which then the algorithm derives the next digit of pi. And on the left, we have the Python function, and on the right, we have the translated Julia function. And let us see what happens when we try to run this on one of the iterations of the program. And as you can see, K2 is the same on both Python and Julia. And after the first operation, the variable ACC is still the same on both Python and Julia. However, when we try to move on to the next assignment, the value of ACC on Julia is the result of an integer overflow. Now, unfortunately, detecting whether arbitrary precision arithmetic is necessary is not something that the transpiler can detect at compile time, as it is impossible to statically predict the values of variables. So going back to our first code excerpt of the function main, what we propose is that the programmer provides information regarding whether the variables are required to use arbitrary precision arithmetic. And we allow the programmers to do so through the use of type comments. And with these annotations, transpiler now generates the correct code for this use case and hence avoiding the overflow scenario. Now, it is also relevant to measure the performance impact of using arbitrary precision arithmetic, and we measured the transpiled code and compared it against a reference Python and Julia version, where the reference Julia version is also using arbitrary precision arithmetic. Now, as we can see, Python takes around 2.6 seconds to execute, and both the translated Julia version and Julia's reference version take around 1.5 seconds, which is an improvement from the result we had in Python. Now, after dealing with those initial mismatches, we wanted to evaluate PyJL's capabilities with larger code samples, and we also wanted to evaluate what performance we could get by translating those code samples. And therefore, we have selected performance benchmarks in Python, which also have a Julia implementation created by Julia programmers, which we will regard as the reference implementation. And these reference implementations use Julia's performance features and represent the best case scenario for a given benchmark. Now, the first test case is the n-body problem, and this predicts the interactions of the Jovian planets in our solar system. Now, in this case, we have chosen this particular implementation as it can be used to compare the performance of iterators in both languages. Now, if we analyze the performance results, we see that Python takes around 346 seconds, but what is surprising is that Julia takes around twice as much time, which, given the performance of its iterators, was unexpected. And to understand what caused these results, we decided to profile the generated Julia source code, where we found that a function in particular was consuming a lot of memory. Now, that function is the combinations function, and on the left we have the Python function, and on the right we have the result of transpiling that function to Julia. And this function generates combinations of objects that it receives from an input list, and it returns a list containing the result of those combinations. Now, this resulted in the generation of generic Julia source code, which, in the case of generic lists, results in a large overhead in Julia. And by annotating the Python source code, we can improve the performance, as the annotations now get translated to Julia. Now, the improved performance from this change has to do with the fact that the vector can now be allocated contiguously, resulting in improved lookup speed. Now, after the optimization, we get a result which is almost 8 times faster than Python. And regarding the reference Julia implementation, it is relevant to mention that it is highly optimized and takes advantage of Julia's performance characteristics, such as loop unrolling or skipping bounds verification in loops. Now, moving on to our second use case, we have the FASTA benchmark, which generates random DNA sequences by using a linear congruential generator. And it also offers an opportunity to test the translation of generator functions in Julia. Now, let's start this evaluation by comparing the two methods offered by the transpiler to translate Python's generator functions. Now, on top, we have the Python function genRandom, which generates random numbers by simulating a linear congruential generator. Now, generator functions in Python implement the producer-consumer pattern, and in Python, they're implemented using a finite state machine. Now, on the left, we will show the translation of this function using channels, and on the right, we will show the translation using resumables. And as we can see, the function definitions stay the same on both implementations, and so does the remaining body of the function. It is when we come to the yield statement that both implementations change. Now, on the left, the transpiler creates an unbuffered channel in Julia and then adds the elements to the channel. And when using resumables, the function has to be annotated with a macro indicating that it's a resumable function, and it then uses a yield macro to produce the value. And similarly to Python, resumables is also implemented using a finite state machine. Now, despite the first solution being the more pragmatic approach in Julia, the main reason why we offer the second option is for performance reasons. And when it comes to performance, the Python version takes around 47 seconds to complete. However, when we transpile this to Julia using channels, the result takes around 7 times longer. If we, however, use the resumables package, this now becomes as fast as Python. However, we can further improve this version to make it run faster than Python. And similarly to the n-body problem, we found a case that used generic vectors, and on the left we present the Python function make cumulative, and on the right we present that function translated by the transpiler. And this function calculates cumulative probabilities from the predicted probabilities of choosing each nucleotide in a DNA sequence, which is represented by the table argument. So the list P will store the cumulative probabilities, while the list C will store the respective nucleotides. However, in this case, both of these vectors are generic, which affects performance in Julia. And simply adding annotations in the Python source code, in the similar way that we did in the n-body problem, and translating this example again, yields better performance. And we now get a time that is 1.36 times faster than Python. However, the Julia reference version is orders of magnitude faster than our translated version, and this is due to several factors. For instance, it stores the random number using a memory reference, eliminating the overhead of creating a finite state machine. Furthermore, it also uses Julia's more efficient data structures. For instance, it replaces strings for vectors holding uint8 values, which is much faster in terms of indexing, and it is therefore a fundamentally different implementation and cannot be compared directly to the translated version. Now, the last example we chose is from the book Neural Networks and Deep Learning from Michael Nielsen, and the main goal is to build a neural network capable of identifying numbers from a MNIST dataset. And this is a large dataset containing handwritten digits typically used to train image recognition and processing systems. What makes this test more challenging to translate is the fact that the image data is represented as NumPy and dimensional arrays. When translating Python functions to Julia, one has to account for the fact that some functions in NumPy have different outputs depending on the types of their inputs. Take the function NumPy dot as an example, which calculates the dot product of n-dimensional vectors. If we have two arrays with one dimension each, this function calculates the inner product of the vectors, and we get the following result. If we now translate this into Julia and perform the same operation as in Python, we get the same result. However, if we try to execute the same operation on two-dimensional arrays, it will now perform matrix multiplication. And if we try to translate this to Julia using the same dot operator, it will return the same result as we've seen before. Therefore, we need to use the standard multiplication operator if we want to get a similar result in Julia. There is, however, one mismatch, which is that NumPy functions can return a different view of the stored matrix. That is, despite the memory buffer being the same, the result may be represented differently. As an example, consider the following function which evaluates the resulting output from the neural network against the expected output. The function feedForward processes the data and outputs a 10-dimensional array, where each index corresponds to the evaluation of a number in the MNIST dataset, so from 0 to 9. Then the argmax function retrieves the final output from the neural network, which in this case is the index with the highest probability. Now, the issue is that the argmax function will find the corresponding index in the flattened array, and therefore it will select index 7 and use that value to compare against the expected result. If we try to translate this to Julia, we will not have the same result. Instead, the function argmax in Julia will retrieve the index in Cartesian form. And to solve the first problem, Julia offers a custom syntax which flattens the array, and to ensure that that operation does not have a performance penalty, the transpiler creates a view which also prevents redundant memory allocations. Then we also need to decrease the resulting value by 1 as Julia uses 1-based indexing, and after that the result is now correct and matches Python's result. Now let us go back to the original Python examples to introduce one more mismatch. If we want to multiply both matrices A and B without using NumPy's dot function, we can use the multiplication operator. However, the results are very different from the ones that we've seen before while using the dot product. Notice how they also differ from Julia's multiplication operation. And to demonstrate how we can map this to Julia, we first need to deal with another mismatch. And this mismatch involves the concept of broadcasting, which applies operations element-wise on array-like objects. To demonstrate how broadcasting works, in Python and Julia, we have the sigmoid function. And in Python, broadcasting will happen automatically. Notice that the function uses a binary operations between scalars and NumPy n-dimensional arrays. To translate this to Julia, the transpiler uses the dot syntax. Let's follow the translation process step by step. Now the transpiler starts from the inner binary operation, and it translates the function call to NumPy's exp function by propagating the power operation with Euler's constant throughout the matrix. Next, the transpiler detects that there is a binary operation between a scalar and an operation that returns a matrix. Therefore, it applies the broadcasting to the binary operation. And lastly, the transpiler detects that there is a write operand that contains a nested binary operation that is also performing a broadcast, and as the left operand is a scalar, it also applies the broadcast to the division operation. Using broadcasting also works with function calls. As an example, consider the function sigmoid prime, which calculates the derivative of the sigmoid function. Notice, however, that the transpiler does not apply the broadcasting to the binary operations, and this is because we are missing the annotations for the return type on the sigmoid function. And by annotating the function's return type, we now get the correct translation. And this once again shows the importance of function annotations. Now, if we now go back to the example we had, we can now complete it with the corresponding broadcasting operation, which gives us the expected result. Now, finally, we want to go back to the translation of negative indexing and demonstrate its use with an example. Now, on the left, we have a Python excerpt which stems from the backpropagation step of the neural network. And notice how it uses negative indexing throughout the for loop. However, this case can be translated to Julia, as the transpiler knows at compile time that the range will always be a positive value. That is, it has a positive start given by the constant value of 2, and it also has a positive step value. Now in Python, omitting the step parameter in the range function gives it a default value of 1. Therefore, this code excerpt is translated by the transpiler as follows, and the translated code uses the end keyword to index the array backwards. Now, to conclude, we have some thoughts on the current status and about the future of PyJL. Now, throughout the process of building the transpiler, as examples got more and more complex, code analysis has increasingly become a focal point in the development of the transpiler. Many translation scenarios will require the transpiler to assert certain properties on the code. As a simple example, consider the case of negative indexing we just seen. And this area is still something I would like to explore in the future and find more formal methods and proofs to verify code behavior. Another aspect that has improved since the beginning but still requires some work is the inference mechanism. Now, integrating an external mechanism such as PyType into Py2Many would be beneficial, especially for its interprocedural inference capabilities, allowing us to infer types beyond the scopes of functions. In terms of our plans for the future, we definitely need a larger regression test suite to cover more of Python's standard library. Furthermore, we would also like to assert the capabilities of the transpiler with module imports, and this has already been tested outside the regression test suite, but requires a more rigorous testing. And lastly, the idea of the meta-transpiler, where a transpiler transpiles itself to the target language, is now more present than ever, but still very much a work in progress. There have been some ideas regarding this topic. While discussing this with one of Py2Many's maintainers, we concluded that we will most likely first have to create a Python to Python transpiler to reduce the working subset to a more manageable subset of Python. And this would then serve as input for the transpilers, which would only need to work in that manageable subset. And that concludes our presentation. Thank you all very much for your attention.